All right, so now we're going to do the left-hand sum. Same function, same interval. All right, so you can probably do this pretty much on your own, but I would stop at number 3 to check in, because how to do this, there are different ways to do it, and I want to keep us all on the same page. So check in with your number 3, make sure you do it the way I did. Okay, hopefully you've had a chance to look at those. So now our number 1 question is, what is delta x? Well, delta x hasn't changed between the left and right hand sum. Delta x is the same. It's just 2 over n. I've drawn a picture here of the left hand sum, and we want to bear in mind that the left hand sum underestimates an increasing function. Before, we were doing a right-hand sum, which overestimates the increasing function. And by the way, it's opposite for a decreasing function. So for a decreasing function, the left hand overestimates and the right hand underestimates, and that's a good thing to know. All right, but we have a left-hand sum, an increasing function, so it's underestimates, so that means our true area is actually greater than our sum of f of x sub I delta x. Now this looks like the same expression from the previous problem, and it kind of is, but the x sub i's are different now because I'm using the left hand of each interval instead of the right hand. So now the x sub I is over here instead of over here, and that's going to make a difference in what we have. So for number 2, like what that difference looks like, and here's what I want to contrast to the way I usually do Riemann sums if I'm just doing a finite Riemann sum. I will usually pull the trick when I'm doing that of calling the first x x0, and then using x0, x1, x2, and so forth up to x sub n minus 1. All right, that's what I like to do. And it makes calculating finite sum easier. However, our summation formulas don't go from 0 to n minus 1. They go from 1 to n. And so that's going to make a difference when we go to use these sums to convert the formula that we get. By the way, there are ways to do it by using 0 to n minus 1 for your index variables. It's not that hard to modify this formula to account for that, but that's the trade-off. You would have to modify this formula, and then you get easier x sub i's. All right, I decided to keep the x sub i's a little more complicated so we can use the same formula. So what I'm saying here is, instead of x0 equals 0, I'm going to say x1 equals 0 and x2 equals 2 over n. Remember, in our right-hand sum, we said x1 was equal to 2 over n. These x sub i's are different from the other x sub i's. They have to be, because of the only thing that's different in this formula. Otherwise, the left-hand sum and the right-hand sum will be the same. They can't be. So the x sub i's must be different. They can't be the same as the x sub i's from before. All right, so, all right, but again, you could keep the x sub I the same and do I equals 0 to n minus 1, but that throws a different monkey wrench in the works. So I chose to go with this monkey wrench. All right, x sub 2 equals 2 over n, x sub 3 equals 4 over n, x sub 4 equals 6 over n, and so on. So if that's not what you put for this, think about how you really want to do the x sub I formula. All right, so for the x sub I formula written with these this way, this is I equals 1, I equals 2, I equals 3, I equals 4. How am I going to generate this expression from these i's? Well, if you figure that out, you figured out that it's 2 I minus 1 over n. You can check that, it'll give you that. Some people, by the way, just say, you know what I'm going to do? I'm going to take the prior x sub i's, and the only difference is that I'm subtracting delta x off all of them, so minus 2 over n. So some of you guys might have written it this way, which is fine. You can see algebraically that's the same as this. I'm going to go with this one because it's going to make some of our subsequent work a little clearer. All right, so now that everybody's on the same page with this expression for x sub I, now go ahead and do number 4 through 6. All right, I'm assuming you have now done number 4 through 6, so I'm going to do number 4. It is f of x sub I. So we already know that f of x is x squared. That hasn't changed. So f of x sub I is x sub I squared. But then that's a little trickier to do with this. So I have to go 2I minus 1 over n squared. All right, so we're going to simplify that a little bit. So I'll just square each of these terms separately. 4I minus 1 squared over n squared. Of course, you could square out this I minus 1. Eventually, we will have to, but I'm going to leave it for now. It's a little more compact as is. All right, so number 5, what is the a sub I? So the area sub I is f of x sub I delta x. So that's equal to, here's my f of x sub I right here, so 4 times I minus 1 squared over n squared, times my delta x, which is 2 over n, times 2 over n. All right, so I guess I'll put this down here, 8 I minus 1 squared over n cubed. All right. So now, for number 6, I know that the area from the left for any number of rectangles on this function on this interval is equal to the sum from I equals 1 to n of 8 times I minus 1 squared over n cubed. So the next thing to do is to use these formulas to convert this into something we can do the limit as n approaches infinity of. But in order to do that, we need a little bit of background first. So that's what's coming up next.